Good day, ma'am, and to everyone. So we are the Group 5. I am Raven Gomez, together with Warren Gonsalvo, Jericho Hakuda, Vincent Luis Hernandez, Mariel Hernandez, and Miguel Leandro Hoson, here to present to you a research group activity entitled Comparative Analysis of R-1234yf in Commercial Refrigeration Systems. And for the introduction part, it would be tackled by Warren Gonsalvo.
Here is the brief overview. In various fields including industrial, cold chains, residential and commercial structures, etc., the refrigeration system is essential. It maintains food or medication at a proper temperature, gives buildings thermal comfort, and is necessary for some industrial operations like air liquefaction. Refrigerant focus. R-1234yf is a refrigerant developed as a likely replacement for tetrafluoroethane, which is a widely used refrigerant that is highly global warming contributor. It is mostly used in mobile air conditioning system and heat pumps. The aim of this research is to analyze the potential reduction of the global warming as R-1234yf is a potential alternative refrigerant which is more environmentally friendly than its counterpart R-134a. Its commercial application, performance, and cost will also be evaluated throughout this research to further nurture the knowledge of the researchers in this particular refrigerant.
Overview of refrigerants properties. Refrigerant name. R-1234yf is a refrigerant gas that used in air conditioning systems and heat pumps. It is an attractive solvent for selective extraction and biopharmaceuticals, offering a low global warming potential. Thermodynamic properties. Boiling point, 243.75 Kelvin. Critical temperature, 367.7 Kelvin or 368.15 Kelvin. Critical pressure, 43.382 megapascal. Commercial refrigeration system which shield and preserve perishable goods depends heavily on refrigerants. Many companies are switching to greener alternatives as a result of refrigerant restriction that phase out ozone-depleting refrigerants like R22. When it comes to replacing your freezer or refrigerator, knowing the many kinds of refrigerants that are available for commercial use will help you make an informed choice.
Next, we move on to the environmental impact, which is the DWP and the ODP. The global warming potential, or the GWP. R1234yf has a global warming potential rating of less than 1, while R134a has a GWP rating of 1,430 for AR4 and 1,390 for AR5. And R404A has a GWP rating of 3,921.60 for AR4 and 3,942.80 for AR5. R1234yf has a low GWP because it is classified as a hydrofluoroolefin or HFO, meaning it is chemically unstable and rapidly breaks down in the atmosphere. On the other hand, both R134A and R404A have a high GWP because they are known as a hydrofluorocarbon or HFC, meaning it is a potent greenhouse gas that traps more heat in the atmosphere, higher than that of CO2. Next is the ozone depletion potential or the ODP. All three refrigerants have an ODP rating of 0. This is because all mentioned refrigerants possess an ODP of rating of 0. This is because none of these refrigerants contain chlorine, which is the chemical responsible for ozone depletion. Now we move on to the environmental benefits of R1234yf. The R1234yf refrigerant has the ability to decompose into a harmless component, including carbon dioxide and trifluoroacetic acid. It has a high energy efficiency, which results in less electricity consumption, which in turn lowers the emissions of power plants. It has a lower carbon footprint due to low greenhouse gas emissions and increased energy efficiency. And it cannot deplete the ozone layer because it does not contain harmful chemicals like chlorine or bromine. Next, we move on to the performance in commercial refrigeration systems. First, we have the cooling efficiency. In a study that used the R1234yf and the R134a refrigerant, its results showed that the R1234yf has a lower cooling capacity than the R34a, about 5 to 10% lower to be exact. However, when modifications were made to the system using the R1234yf as a refrigerant, the results were narrowed down, almost becoming similar to one another. Then, the energy consumption. When evaluated using the COP and steady-state energy consumption, R1234yf demonstrates energy efficiency that is very similar to R134a. In optimized systems, the COP typically varies by only about 3 to 4%, and the energy consumption figures are nearly identical. As a result, R1234yf emerges as a practical, low GWP alternative that maintains performance, making it a compelling choice for commercial refrigeration applications where both energy efficiency and environmental impact are critical. Lastly, the system compatibility. R1234yf generally performs similarly to R134a in terms of cooling capacity and energy efficiency. But because its thermodynamic properties and mild flammability differ from R134a, some adjustments are often necessary. In systems originally designed for R134a, minor modifications such as the thermal expansion valve, adjusting compressor controls, and optimizing piping layouts to accommodate slight differences in pressure drop can ensure that the R1234yf operates effectively. Additionally, because R1234yf is classified as A2L or mildly flammable, components such as fittings and service equipment must meet specific safety standards.
We will now proceed to the cost and practical consideration. Next slide, please. For the initial cost, the price of HFO123YF varies depending on the quantity purchased. In bulk purchases by vehicle manufacturers, it costs around $75 to $80 per kilogram, while it is approximately $250 to $350 per kilogram in small-scale purchases by Mac services. The production cost of HFO123YF ranges from $7,000 to $15,610 per ton, considering raw materials, energy, and capital recovery costs. For automotive applications, the refrigerant charge varies based on vehicle type. For $75 to $80 per kilogram, with about 0.5 to 0.7 kilogram used to charge passenger cars, up to 2 kilogram for large vehicles, and up to 5 kilogram for mining and agricultural equipment. However, new system using HFO123YF may require less refrigerant due to design improvements. For the operating costs, maintenance costs are estimated at 3.2% per year of fixed capital assets. Additional operating costs, including labor, supply, overhead, insurance, marketing, and general administration, can increase total expenses by 75 to 150% beyond the base production costs.
In system modifications, one of the critical components that must be considered is the heat exchanger. R-1234yf possesses various thermal characteristics compared to 134 air. To preserve efficiency, systems can require more effective heat exchangers. For instance, condensers and evaporators, which are capable of managing the new refrigerant's behavior characteristics. Some designs incorporate an internal heat exchanger or IHX to enhance subcooling and system efficiency. Adding an internal heat exchanger or IHX has been shown to reduce performance losses when switching from R134A to R1234YF. Another one is the compressors. R1234YF is compatible with traditional compressors but may slightly vary in performance. Studies have shown that with R1234YF, compressor discharge temperature ranges from about 6 to 7 degrees Fahrenheit lower than with R134A, making it a relatively easy substitute. In some cases, it needs potential adjustment in speed to optimize performance. Expansion devices such as expansion valves and other metering devices may require minimal modifications to accommodate R1234YF pressure and flow characteristics. Some systems benefit from using an ejector-based expansion device to improve energy efficiency. Lubrication compatibility is also one of the things that need to be considered. R1234YF is also largely compatible with the current polyalkylene glycol or PAG lubricants employed in R134A systems. Testing and verification may, however, be necessary in certain instances to ensure lubrication and system reliability over the long term. In drop-in replacement feasibility, R1234YF is a drop-in substitute for R134A in most systems with slight adjustment only. It has a lower discharge temperature, approximately 25 to 40 degrees Fahrenheit, lower than R134A, which minimize compressor stress and enhance reliability. And it also has limitations. R1234YF cannot directly replace R410A in high pressure applications like heat pumps due to lower heating and cooling capacity. While it works well in automotive air conditioning or MAC systems, some systems optimizations are needed to ensure maximum efficiency and performance. In terms of long-term savings, HFO1234YF is mostly used in new passenger cars and become in demand in residential refrigeration due to its energy efficiency, reduced environmental impact, and regulatory compliance. Second, optimized R1234YF system, particularly those with IHX, are capable of attaining performance levels similar to those of R134A systems, resulting in possible energy savings. And the third one, R1234YF possess a low global warming potential or GWP complying with strict environmental regulations. The use of this refrigerant can help lower potential compliance expenses related to higher GWP refrigerants.
For the safety and handling, we first have the safety concerns. Next slide. Flammability. According to ASHRAE 34 or ASHRAE 2007, the flammability of R1234YF is categorized as A2L with low flammability and low burning speed. R1234YF is considered to have mild flammability and pose a low risk of explosion. Toxicity. R1234YF may cause acute toxicity resulting in allergic skin reactions, and respiratory irritation. It may also irritate the eyes and skin and be harmful if swallowed. Next we have is the pressure. Operates at pressure similar to R-1334A but requires proper handling to avoid leaks. Next, decomposition risk. Under extreme conditions, such as exposure to high temperatures or open flames, R1234yf can decompose and produce hazardous byproducts, including hydrogen fluoride. Now we have the regulations. The ASHRAE Standard 34, it classifies R1234yf as A2L, which is low toxicity and mildly flammable. SAE J2845 provides guidelines for technician training on the safe handling and service of mobile air conditioning systems using R1234yf. Then we have the OSHA, or Occupational Safety and Health Administration. It requires proper ventilation and personnel protective equipment, or PPE, when handling refrigerants to prevent suffocation and frostbite. We have the EPA SNAP, or the Significant New Alternatives Policy Program, approves that the R1234yf as an acceptable substitute for ozone-depleting substances in motor vehicle air conditioning systems, subject to use conditions. Now, we have the mitigation measures. First, avoid breathing mist or vapor and contact with eyes, skin, and clothing. Next, apply proper sealing techniques and inspect regularly for leaks to reduce flammability risk. Third, provide proper ventilation to avoid the accumulation of flammable gas mixtures. Then, employ SAE compliant tools and recovery equipment when handling R1234yf to permit safe handling and servicing. Next, we have keep R1234yf away from ignition sources, heat, and open flame. Use non-sparking tools and keep fire extinguishers handy. Then, train technicians on the proper handling of R1234yf and mandate the use of appropriate PPE, such as gloves and safety glasses, to prevent frostbite and other injury. Lastly, equip commercial applications with leak detection systems and automatic shut-off valves to make R1234yf safer to use.
Next we have are the real-world application and case studies. The first case study. R1234yf is proposed to replace R134A as an alternative environmental friendly refrigerant used in automobile air conditioning systems. Several automobile companies including Mercedes-Benz, BMW, and VW Audi tested the use of this refrigerant. This refrigerant was classified as highly flammable for several years until SAE proved that this refrigerant will not cause fire under conditions normally experienced by a moving vehicle. However, the above-mentioned automobile companies reported that if the refrigerant is sprayed into the AC compressor, upon collision it will cause ignition. With this, Mercedes-Benz, BMW, and VW Audi left the SAE R1234yf CRP team, stating that the tests done were not enough to judge the safety of the refrigerant to be used in the vehicles. In the maintenance aspect, the R1234yf can be handled in repair shops that repair R1234A, although it would require different specialized equipment to perform the services.
Case study 2. Refrigeration and air conditioning system are essential in modern society and refrigerants play a crucial role. Traditional refrigerants like CFCs and HCFCs have harmed the environment, causing ozone depletion and contributing a global warming. As a result, there is a growing interest in developing environmentally friendly refrigerants with low global warming potential, GWP. and no ozone depletion potential, or ODP. This review discusses natural refrigerants, NH3, CO2 hydrocarbons, hydrofluorolefins, HO, and HFCs with ultra-low GWP, hydrofluoroders, HFEs, and blends of these. The article compares their properties and recommends promoting natural refrigerants and exploring HFOs, HFCs, and mixture as potential substitutes for more sustainable cooling technologies.
For the outcomes, there are several advantages to switching to eco-friendly refrigerants in terms of cost, energy savings, and environmental impact. Natural refrigerants with higher energy efficiency, such as carbon dioxide and ammonia, result in lower energy usage and running expenses. Because these refrigerants require specialist equipment, the initial expenditure may be expensive, but over time, the savings from reduced energy use may outweigh these expenses. Additionally, because natural refrigerants have very low global warming potential or GWP and negligible ozone depletion potential or ODP, they help reduce harmful emissions and slow down climate change. All things considered, switching to these environmentally friendly refrigerants offers an affordable, long-term answer for air conditioning and refrigeration systems.
In conclusion, next slide please. For the summary, the performance of R1234yf has a 5% to 10% lower cooling capacity than R1234a, but system modification can reduce this gap. Energy efficiency is similar to R134A, with only 3 to 4% difference in COP when optimized. System compatibility requires minor modifications such as adjusting expansion valves and compressor controls. In costing, the initial cost of HFO1234yf costs $75 to 80 per kilogram for bulk purchases and $250 to $350 per kilogram or for small scale purchases. In the operating costs, maintenance costs are assets, with additional costs increasing total expenses by 75 to 150%. And on the long-term savings, compliance with environmental regulation reduces potential future costs, and optimized systems can achieve energy savings. On the environmental impact, R1234yf has a low global warming potential or GWP because it breaks down quickly in the atmosphere compared to R134a. It is an environmentally friendly alternative that helps meet stricter refrigerant regulations. And for the safety, the flammability classified as A2L or mildly flammable with low burning speed. Toxicity, it may cause respiratory irritation, allergy skin reaction, and eye irritation. Decomposition risk. At high temperatures, it can produce hazardous or byproducts like hydrogen fluoride. For practicality, drop-in replacement for R134A with minimal system modifications, not suitable for high-pressure applications like R410A systems. It complies with ASHRAE, SAE, and EPA regulations, ensuring safe handling and environmental compliance.
Next, we have the recommendation. R1234yf is a viable alternative refrigerant with significantly lower global warming potential or GWP than R134A. Second, it offers similar energy efficiency but requires system optimizations such as internal heat exchangers or IHX to match performance. Third, despite higher upfront costs, R1234yf's environmental benefits, regulatory compliance, and comparable performance make it a strong candidate for widespread use in commercial refrigeration, provided safety measure and necessary system modifications are implemented.
Future research. Refrigerant blends and development. Explore new refrigerant mixtures to enhance performance while maintaining low GWP. System design enhancements. Improve heat exchangers, ejector-based cycles, and expansion valve design to optimize efficiency, energy efficiency, and cost optimization. Study internal heat exchangers, IHX, AI-driven system controls, and life cycle costs to reduce operational expenses. Safety and environmental impact. Investigate R1234yf decomposition, risk, advanced leak detection, and environmental effects. Regulatory and policy advancement. Assess global adoption, industry best practices, and regulatory trends for wider implementation.
And for the last part of our presentation, here are the list of references where we have gathered all the information about our research. That's all for our group presentation. Thank you for listening.